Well, hello guys, here Mr. G with another video. This time we're going to be working with the grade 12 and we're going to be solving a question and answering a question on rate of reaction. This one was question 5 from the question paper done at the Eastern Cape in 2023, paper 2. I'm going to leave the question in the description below so you can answer the question before watching the video, and before we answer the question, don't forget to subscribe for the channel. The question says a group of learners investigate the relationship between reaction rate and concentration. They use the reaction between calcium carbonate powder in an excess hydrochloric acid. So hydrochloric acid is in excess, you have too much, and calcium carbonate is a limiting reagent, and this happened at 25 degrees Celsius. The balance equation for this reaction is, and they are giving you the reaction there. In this reaction you can see that delta H is negative, and therefore this one is an exothermic reaction. It may not need it, but it's good to recall that one. Okay, the apparatus used is illustrated below, and you have this apparatus in which the reaction happened here. The gas is going to go up the conical flask, or the gas will go here and eventually will go through this tube all the way to the syringe, and the gas were collected there. The table below shows the reaction condition for experiments 1 and 2, and you have the two conditions here, the two experiments in which they change the concentration, as you can see there. Question 5.1, define the term reaction rate. And here is the definition. Reaction rate is the change in concentration of reactants or product per unit time. That is important here. The change in concentration of reactant or product per unit time. If you say that, guys, you will get 2 marks. It's quite simple. It's a definition that everyone can learn. Name the apparatus needed for this investigation that is not shown in the sketch above. Alright, so let's go to the sketch, and there is something important that we cannot see in the sketch. Guys, we are taking the time. We're taking the time, however, you don't see here a stopwatch. Stopwatch is important. It should be somewhere here. It should be a stopwatch there. Let's say this one is stopwatch. I'm not good at painting, but this one is a stopwatch. So the instrument that is not there and is needed is the stopwatch. It's quite simple, however, it could trick you. It could trick you because you don't see it there. Stopwatch is needed, guys. Otherwise, how are you going to measure the time? Give a reason why the temperature of the reaction mixture does not remain constant during the reactions. Okay, let's go back here. The temperature of the system was kept constant at 25 degrees Celsius. Temperature was kept constant. However, this question speaks now about the temperature of the reaction mixture does not remain constant. The temperature within the reaction. Why doesn't remain constant? Because it's an exothermic reaction, and therefore energy is released. Is given off, and that that energy generally is given in the form of heat. Alright, so that means that the temperature of the reaction will change, and that is why it is changing. It's exothermic and energy is released. And that is all you have to say. If you say that, you'll get another mark. So reaction is exothermic and release heat. So far, 2, 3, and 4 mark, guys. Next question. Will time y for the experiment 2 be lower or shorter, longer or shorter than 2,28 minutes? Well, the concentration is higher, and remember, the higher the concentration, the faster the time the reaction will happen. Therefore, the lower it will take here. So this one will be shorter time. Shorter time, and if you say that, you will get another mark. Oh, come on, guys. Here, so far, we can get a lot of marks for this question. It's quite simple. Question 5.5, explain your answer to question 5.4 by referring to the collision theory. Now we have to explain. And then let's go to a new page for that question. Okay, so higher concentration means more particles per unit volume. Remember, concentration is equal to number of mole divided by volume. So within the same volume, you will have more particles. As a result of having more particles, you will have therefore more collisions with correct orientation. As you have more collision, there will be more probability of collision with correct orientation. If you say that, guys, you will get 1 mark. So you will get 1 mark for saying more collisions with correct orientation. You don't have to say everything I am saying here. I'm trying to explain to you. Then you have to say that, therefore, the number of effective collision per unit time increases. So if you don't write per unit time, you don't get that other mark. This question have 2 marks. You have to say per unit time. Effective collision per unit time increases. Therefore, the rate of the reaction increases. Okay, so that is how you explain this one using the collision theory. And that was quite simple. Let's go to question 5.6. Now, question 5.6. In experiment 1, exactly 250 cubic centimeters of carbon dioxide is produced in 5,28 minutes. Calculate the average rate of production of calcium carbonate and calcium dioxide in centimeter cubic per minute. So when you do this one, you always come here to look at the unit. So what do they want? They want the change, the rate of the reaction in terms of volume. You want to calculate how fast this volume is being produced. So the rate here is going to be equal to the change of volume produced divided by the change in time. Alright, this is final volume minus initial volume divided by final time minus initial time. Okay, so what is final volume here is 250. Let me write that 250 probably. 250 cubic centimeter minus initial, which is 0. Initially you didn't have any gas produced. The time was 5,28 minutes. So the final time is 5,28 minutes. The initial time is 0. And when you calculate that one, here you will get 47,35 centimeter cubic per minute. There we go. And that is the answer. So if you do this one, you'll get 1 mark for the substitution of the 250, 1 mark for the 5,28, and 1 for the final answer here. Okay, next question. Shortly after the reaction in experiment 1 is complete, the flask is sealed tightly, and it is found that 100 cubic centimeters of carbon dioxide has escaped out of the flask. Calculate the mass of carbon dioxide remaining in the flask after the flask is sealed. Take the molar volume of carbon dioxide at 25 degrees Celsius to be 25,000 cubic centimeters per mole. So there is some stoichiometric involved here. Now here what we need to know, this is the molar volume for this gas at this specific temperature. Okay, so this question is quite simple. It's not that bad. Guys, we know that 250 were collected or were produced. This one was not collected, was produced. It doesn't say anything about collected. So we know that we have produced in 5,28 250 cubic centimeter of gas is produced. And we also know that 100 has escaped. Alright, we know that 200 is being produced and 100 has escaped. So how much is remaining there? Which is the question. How much of this one is remaining? How much is in terms of volume, how much is remaining? Well, it's 150 cubic centimeters is remaining. This one is remaining. We know that this one is remaining. Alright, now how do we do that? And this is quite simple. 250 minus 100 is equal to 150 cubic centimeter. This is what we calculated. So now we know how much of the gas in terms of volume, how much volume of the gas is remaining behind. Now they want to know the mass. How we do that? First of all, let's calculate the number of mole. But just for you to know how to calculate that mass, number of mole is equal to mass divided by molar mass. But we do not have the number of mole. We do not have this number of mole. So we are going to calculate the number of mole. Number of mole is equal to volume divided by molar volume. They giving us the molar volume, and the volume that is remaining, we did calculate it here, is 150 cubic centimeter. So number of mole is equal to the volume that is remaining behind, which is 150 divided by the molar volume, which is 25,000, okay, cubic centimeter per mole. And that will give you that the number of mole is equal to 0,006 mole. Now we can take this one and substitute in there and calculate the number of the mass, which is what they asking us. I think it's enough space to do it in this side here. So let's do it here. Let's rearrange. It's quite simple. It's equal to number of mole multiplied by molar mass. This is equal to number of mole 0,006 molar mass of carbon dioxide. Let's calculate it as well. So this one is, for carbon, is 12 plus 2 times 16. That will give you the answer. And this will give you 0,264 grams. That is the mass of the gas that is remaining behind. And then, if you do this one, guys, you get marks. The first mark you get here is for calculating this gas, the volume of the gas remaining. This one will give you 1 mark, and it's quite simple. One is for calculating the number of mole, but they're giving you the mark for the substitution there. Another mark is going to be for this substitution here, and then the other mark is for the final answer. It's 4 marks. The question is not that difficult. It's a good question. Let's go to question 5.7. In experiment 3, the learners now add 50 cubic centimeter of excess ethanoic acid solution with a concentration of 0,9 mole per decimeter cubic to the calcium carbonate powder at 25 degrees Celsius and compare the result of those of experiment 1. The graph of volume of carbon dioxide against time for the 2 experiments is shown below. So here we have Q and P. Alright? Alright. Now, which graph P or Q represent the result of experiment 3? Now, what is the difference of experiment 3 with the previous experiment? And let's maybe write it here. In experiment 1, they use HCl. Alright? In experiment 2, they use HCl. They change the concentration. In experiment 3, they use ethanoic acid, C2H4O2. They use ethanoic acid, okay, with a concentration of 0,9. If we go back here, we're using exactly the same as the experiment 1 and the same volume. So in this case, they use the same concentration of experiment 1 and experiment 2. Both of them have the concentration of 0,9 mole per decimeter cubic. So let's write here 0,9 mole per decimeter cubic. Let me just fix it here. This one is, you know what, I'm going to move all this one a little bit here because I want to write that one there. This one is 0,9 mole per decimeter cubic. This one is 0,9 mole per decimeter cubic. Now, what is the thing? The concentration is the same. So what they change? They change the strength of the acid. They use different acid. They use now ethanoic acid, and previously they used hydrochloric acid. So what we have to go here to know? Now we're going to acid and bases. You need to remember that hydrochloric acid is a strong acid, is a strong acid, and ethanoic acid is a weak acid. Okay, that is important. We are comparing a strong acid with a weak acid with the same concentration. So now, which graph P or Q represent the result of experiment 3? Well, it will be P. P will represent experiment 3. Alright, and Q will represent experiment 1. That is the thing here. So if you say that, you'll get 1 mark for saying that is experiment 3. Explain your answer in question 5.7.1. And guys, the explanation is more or less on this point here, where you have to say that ethanoic acid is a weak acid okay, which result in lower rate of reaction. So this here, the weak acid, we have lower rate of reaction. You can see that have a smaller gradient, okay? You can see that have lower gradient. This one have gradient. Okay, if you say that, guys, now the marks are one for saying it's a weak acid or it's weaker than hydrochloric acid, and one for saying that have lower rate of reaction. Is not that bad, that question. How does the amount of calcium carbonate used in experiment 1 compare to the amount of calcium carbonate used in experiment 3? Choose larger than, smaller than, or equal to, and give a reason for your answer, and that will be the end of the question. And then we have to come to the graph, and then you can see that they end at the same point. So you can see that the volume is the same volume of CO2 produced. Okay, therefore the amount of calcium carbonate they used was exactly the same. How we know that? Because the final amount of carbon dioxide is the same. The final amount of CO3 is the same. And guys, this is the end of the question. 1 mark for saying equal to, 1 for saying that the final amount is the same. It's a nice question, it's a long question, and it's a lot of things. I hope it helped, guys. Thumb up, try to solve the question before watching the video. The video is helping you to just mark. Thank you for watching. Thumb up, subscribe for the channel. Next time we're going to be working with equilibrium, which is this question 6, and don't miss that video. I'll see you next time. Mr. G here.